This conference will now be recorded.
Hello, everybody. Jordan Girth here with the National Weather Service Office of Observations. Thank you so much for joining us for the Satellite Book Club Seminar Series. This is session number 186. The title of today's presentation is GLM Gridded Product Analysis of the February 27 and 28, 2024 tornado outbreak. I'm pleased to have our presenter for today is Joseph Patton from the Cooperative Institute for Satellite and Earth System Studies at the University of Maryland, College Park. Following his presentation, we'll have discussion facilitated by Steve Flegel, Science and Operations Officer at the National Weather Service Forecast Office in Aberdeen, South Dakota. As you just heard, this session is being recorded, and as always, there's an opportunity for Q&A after the presentation. If you have signed in with a general account, please note your name when asking a question in the chat so that we can get back to you if necessary. I'd encourage everybody to put their questions in the chat room and we will field them in the order they are asked. We are looking for future presenters. If you'd like to be part of our Satellite Book Club seminar series, please contact Kashad Bowman and Emily Maddox, and the training team can help create training materials that may be unavailable. Ross Van Til with the Office of the Chief Learning Officer can help with that. I'd like to thank our Tower S team, Kashad and Emily, the Office of the Chief Learning Officer, the GOZAR, JPSS program, our presenter, facilitator, and all of you for being with us today and making the Satellite Book Club seminar series a success each and every week. See, we have almost 60 folks on the line today. Without further ado, I'd like to introduce Joseph Patton, who I mentioned is a faculty research assistant at Success at the University of Maryland, College Park. His work focuses on creating training materials and conducting outreach for the Geostationary Lightning Mapper on board the GOZAR series satellites. He previously served as a National Weather Service meteorologist in Goodland, Kansas. Joseph, we're pleased to have you back at the Satellite Book Club today.
Thank you so much, Jordan. It's a pleasure to be here. I appreciate that introduction. You've heard my topic. It's there on the screen, so let's get started. So first, we're going to start out with a little bit of a presentation roadmap to take you, guide you along where we're going to go today. So we're going to start with an event overview of the tornadoes that were reported during this severe weather event. And then we will get into a synoptic and near storm environment analysis with some upper level information from soundings and from the SBC. And then we will also do a walkthrough of several of the tornadoes that were observed from this event. As case studies, we'll go through radar analysis, we'll look at the damage assessments, and then finally we will look at the GOES-16 GLM imagery and then plot some values that were derived from those imagery products from the GLM. After that, we will look through the compiled GLM gridded product values in the 10 minutes leading up to tornadogenesis. And then also, similarly, we'll do the same thing in the 10 minutes after a tornado cessation by comparing the GLM gridded products between all the tornadoes that were observed during this event. Finally, we'll do a comparison with results from the hazardous weather testbed that was conducted in spring 2022, and then we'll end with summary conclusions. So to start out with an overview of this tornado outbreak, there were 21 separate individual tornadoes that were recorded through damage analysis, damage surveys by the National Weather Service forecast offices. The first tornado started at around 23:56 UTC on February 27th, and the final tornado ended around 11:03 UTC on February 28th. So it went well into the early morning hours on February 28th. We can see in this map here in the background, we've got the SBC tornado percent probabilities that were issued that evening. And then the red outlines are the tornado polygon warning polygons that were issued during this event. And then the color-coded damage paths are there with EF0 in blue, EF1 in green, and EF2 in yellow. The counts there on the right-hand side, and we can see that there were 21 total tornadoes, like we said, 3 of which were EF2, 10 were EF1, 7 were EF0, and then 1 was not surveyed. So from the synoptic perspective, what did this event look like? Well, here is the 0Z analysis from the Storm Prediction Center. On the left-hand side, we have a low-level analysis from 925 millibars. I have highlighted here that we can see that there's a strong surface low in the upper Great Lakes, and there's an associated cold front which is approaching from the west to the east, draped across the western edge of the American Midwest. In addition, we've got some abnormally high moisture values with those greater than 12 degrees Celsius dew point temperatures reaching up into the lower Great Lakes area, and some strong moisture advection highlighted there by the green arrows with those southerly winds bringing up moisture and instability into that area. In addition, from the 250 millibar analysis on the right-hand side, we can see we've got a jet streak draped across the central United States, and that has well positioned the left exit region of that jet streak right over that American Midwest region, and that's going to lead to upper level divergence, which will provide broad support for ascent and thunderstorms. Switching gears into a near storm analysis, this is a special 22Z sounding from Springfield, Illinois and central Illinois. This sounding in particular shows greater than 1,000 joules per kilogram of most unstable CAPE and very little SEN, so there's very little that will get in the way of thunderstorm formation later in the day. As you can see, there is a mostly veering wind profile with height, which is favorable for severe weather. We also have steep mid-level lapse rates of greater than 8 degrees Celsius per kilometer, and those lapse rates are very abnormal for this time of year, so very supportive of thunderstorm development. We also have a wet bulb zero height of around 7,500 feet, and that is very supportive of large hail. I don't show this at this time, but from this event in total, there were 86 reports of greater than or equal to 1-inch hail and 6 reports of greater than or equal to 2-inch hail. So this was a severe event that brought tornadoes and large hail. Looking at another sounding from west central Indiana or northwest Indiana in Lafayette, where the University of Purdue is located. This is a special 21Z sounding that was launched by researchers from Purdue, and it also shows a strong veering wind profile with height, as well as ample low-level moisture and relatively steep mid-level lapse rates. We can see that there, from the values on this chart, there are most unstable CAPE values of greater than 900 joules per kilogram, and it didn't even reach the equilibrium level on this sounding, so we can assume that there is even more than that. It did reach up to 6 kilometers, so we do have a good surface to 6 kilometer shear value of greater than 60 knots, which aligns with that left exit region of the upper level jet stream. And then there is a large amount of low level moisture with the low level mixing ratio around 10 grams per kilogram throughout that lowest column of the troposphere. So now let's get into our individual tornadoes now that we have an idea of what the synoptic and near storm environment looked like. This is the first tornado of the event. It was an EF1 tornado near Anawan or Atkinson, Illinois. The radar imagery here is from the closest radar, which was the KLOT Chicago area radar. So this tornado occurred fairly far from the radome, relatively speaking. So we're not going to see any really specific tornado aspects showing up on the radar here, but we do see a strong mesocyclone with strong reflectivity values as the storm moves from west to east. We can see pretty decent rotation right there, and then also we have the local storm reports that were reported at the time to the National Weather Service with large hail and then a couple tornado reports as well. So what did this tornado look like from a damage analysis perspective? Well, like we said, there was EF1 damage recorded between these two towns. It started out with EF0 damage at around 2356 UTC before creating consistent EF1 level damage with winds up to 110 miles per hour, so almost reaching that EF2 level, a very strong EF1 tornado from just north of US Highway 6 all the way crossing over Interstate 80. The picture there in the lower right is from a destroyed farm outbuilding just north of US Highway 6. And then there was also an overturned large semi-trailer on Interstate 80 as well. So some pretty impactful damage for that area. This slide shows the GLM gridded products imagery from that tornado in particular. So we can see that we have flash extent density on the left-hand side. We have minimum flash area in the center, and we've got total optical energy on the right-hand side. So flash extent density shows us our flash counts, and the range there is from 0 to 128. And we can see that as the storm is increasing in severe potential, we can see that there's increase in the number of flash counts. The tornado damage path is also plotted there. I'll highlight it there with my laser pointer right about here, the tornado damage path. And then, so that leads to the minimum flash area product, which we can see there were fairly low values from the convective core of the storm throughout the lifetime of the tornado. And then total optical energy, or the accumulated optical brightness. So basically, of all the flashes that happened, how bright were they in total? We can see that tracks well with the center of this mesocyclone as well. So, just looking at these gridded imagery, it may be hard to compare directly how the values are changing at any particular time. So that is what I'm going to be showing on the next slide. So this slide here is I have tracked the a specific value pertaining to each of the GLM gridded products for each minute in a time series, starting 10 minutes before tornado touchdown and then through 10 minutes after tornado cessation. So the blue value here corresponds to flash extent density, or the flash counts. The blue value is the maximum value of FED that was recorded within the vicinity of the tornado or the storm that caused the tornado. The magenta line is the maximum total optical energy in femtojoules. And then finally, the green line is the minimum flash area value. So the smallest value that was displayed within the MFA gridded product in the vicinity of the tornado. So this was our first tornado of the event. Like I said, the maximum FED value was highly variable in the 10 minutes leading up to tornado touchdown, and then it steadily increased during the tornado life cycle. The minimum MFA values were pegged at their lowest value around 64 square kilometers in this 5-minute window for the lifetime of the tornado, from 10 minutes before touchdown to 10 minutes after cessation. And then we can see that total optical energy generally increased prior to tornadogenesis and then decreased during the tornado. And then we can see that both flash extent density and total optical energy decreased rather quickly after tornado cessation. So we can see that those values dropped off here on the right-hand side of this graph here. So that's one tornado. Let's look at a stronger tornado later in the event and see how that compares to what we just looked at. So first off, starting with a radar analysis, this is from the Springfield, Ohio EF2 tornado. We had, in this particular portion of the event, we had embedded circulations in a convective line of storms. The velocity here in the upper right corner shows strong gate-to-gate shear starting just southeast of Springfield and then tracking to the west to north of London, Ohio. And then again, the correlation coefficient also confirms that we had a tornado signature in this area. We see that there is a tornadic debris signature starting from just southeast of Springfield and then tracking north east towards London, Ohio. So the tornadic debris signature starts here on correlation coefficient and then tracks northeastward. And we can see that there's a good normalized rotation product, which is created within GR2 analysts, showing that rotation as well. So what did this tornado look like from a damage analysis perspective? Like we said, EF2 damage was recorded just southeast of Springfield and then also northwest of London, Ohio. Both of these damages were estimated to have a max wind speed of about 130 miles per hour. The first instance, we can see a picture from a home on Mitchell Road in the Springfield area that was pretty much completely destroyed. And then we can also see in the picture on the lower right, this is from the Madison County Airport north of London, Ohio, and some fairly valuable planes were also completely destroyed by this tornado. So fairly extensive damage, especially for this time of year. Now, between these two damage points, mostly it was just EF1 or EF0 damage that was reported, despite passing over several structures. So we can say with some amount of confidence that the two areas here of EF2 damage were fairly isolated in their nature. So again, what does that look like from a GLM gridded product perspective? Well, the animation here might be a little jerky, but I think you can still get the trends. The long yellow squiggly line is our damaged tornado path, which extends from Springfield off to the northeast. We can see that we have elevated flash extent density values associated with the convective core of that storm. And remember that there is a parallax with the GLM gridded products. So the specific values pertaining to that storm which caused the tornado may be a little bit offset from where your radar display would indicate that you should be putting out warnings and there would be a tornado. And of course, remember that the tornado itself is going to be on that that sort of south central side of the mesocyclone or southwest side of the mesocyclone. So those factors combine to end up with the convective core in the GLM products a little offset to the north and to the west from the actual tornado itself. But that tornado path lines up well with the ongoing warnings at the time, and we can see that there are low minimum flash area values as well as increased total optical energy values associated with the convective core of this storm. So plotting those values out minute by minute, again, the blue line is maximum flash extent density from any of the grids near the tornado. The magenta line is maximum total optical energy in femtojoules, excuse me, and then the green line is minimum flash area in square kilometers. So this was our strongest tornado of the event. It was an EF2 tornado. The maximum flash extent density was relatively constant throughout the 10 minutes prior to tornado genesis, and it was a little bit variable between 60 and 80 flashes per 5 minutes, but it was constant in that it was relatively elevated, especially compared to the other tornadoes in this event. And then one thing I wanted to mention about this graph in particular is that those dashed red lines, those dashed vertical red lines, those indicate the period during the tornado lifetime in which EF2 damage was recorded. So we mentioned that there were those two sort of isolated pockets of EF2 damage, and that's what's being shown by the two red pairs of vertical lines here. So FED and TOE initially decreased during the tornado. We saw that those values kind of dipped down within the first minutes of the tornado, but then they also sharply increased around 1010 UTC when that second pocket of EF2 damage was observed. So that's something interesting to note, that maybe when you have an ongoing tornado that you can tell from a tornadic debris signature is ongoing on radar, that if you see a sudden spike in those GLM gridded products of FED and TOE, that may be a confidence booster for increasing damage severity from that storm and tornado. Again, the minimum MFA value was at its lowest point of around 64 square kilometers for that 5-minute window for the lifetime of the tornado, from 10 minutes before touchdown to 10 minutes after cessation. And then right after tornado cessation, we can see that flash extent density and total optical energy, these blue and magenta lines, they decrease pretty significantly in the few minutes after tornado cessation. So this will be the third and final tornado that we will go through. We will walk through radar and damage and GLM products with. This is a tornado that started near London, Ohio. So if you remember, the previous tornado that we looked at in Springfield ended near London. This is a second tornado with sort of embedded in the same line of storms that started near London and then tracked eastward from there towards Columbus, Ohio. So velocity in the top right shows a noticeable couplet just east of London that moves west-southwest of Columbus, Ohio. We can also see that correlation coefficient was again tracking a pretty significant tornadic debris signature from just east of London to the Columbus area. So that tornadic debris signature gives us confidence that the radar is being able to observe direct effects from this tornado of debris being lofted. And so we're fairly confident there was a tornado going on in that area. And once damage survey teams were able to get out the next day, initially it was just EF0 damage that was reported just east of London where that tornadic debris signature started, but then stronger EF1 damage was reported or assessed a few minutes and miles later to the northeast. The strongest damage was reported to homes along Wilson Road in that area, and that picture in the lower right is from a home in Wilson Road. So you can see that there is some pretty significant roof damage to that home, and then substantial tree damage to quite large in size trees as well. So estimated wind speeds were up to 110 miles per hour, which is just below that threshold for EF2. So it's a very strong EF1 tornado. Looking at the GLM graded products from this tornado, this London, Ohio EF1 tornado, the line of the damage path is this green squiggly line that starts just east of London and then tracks northeast towards Columbus. We can see that there are increased flash extent density values during the lifetime of the storm. We can see that the minimum flash area is decreased within the convective core as the storm tracks from west to east. And then also there are observed increased values of total optical energy, which again is just that accumulated optical brightness from all the flashes that were observed at that time. So if we plot in a time series the three values that we've been tracking, the highest or maximum flash extent density value within the vicinity of the storm, the highest or the maximum value of total optical energy, and then the minimum flash area value, we can see that there was a pretty substantial increase in FED and TOE in the 10 minutes leading up to tornadogenesis. We can see that flash extent density went from around 35 to around 75, and total optical energy went from around 60 femtojoules to nearly 250 femtojoules. And recall that we do have separate y-axes for these products. So the flash extent density is the blue on the left, femtojoules, total optical energy is in the pink, the magenta on the right, and then minimum flash area is in the green on the right. So like we said, maximum FED and TOE increased sharply leading up to tornadogenesis. Our minimum flash area value is again at that around 64 square kilometer value for the lifetime of the tornado from a 5-minute window perspective. And then what we see is that the flash extent density and total optical energy initially decreased during the tornado touchdown, during the actual recorded damage of the tornado, and then they increased as we reached towards tornado cessation. FED showed a pretty significant decrease after tornado cessation, a few minutes after tornado cessation, decreasing all the way back down to about 40 flashes, whereas total optical energy continued to steadily increase and then showed a decrease right there several minutes after tornado cessation. So we do have that signal of those FED and TOE products increasing, and then especially the FED product decreasing after tornado cessation. So now what we want to do is we want to look at, okay, so for all of these 21 tornadoes, what were the GLM trends in the gridded products in the 10 minutes leading up to tornadogenesis, right? Is there a signal of flash extent density increasing? Is there a signal of total optical energy increasing? Well, that's what these two graphs here are showing. So on the left-hand side, we have flash extent density in blue, and we have plotted for all 21 tornadoes the 10 minutes prior to tornadogenesis. The average value is plotted there in black, which is just an average of all 21 tornadoes at each minute. So as we can see, there is a slight increase in FED leading up to tranogenesis, a modest increase of about 2.6 flashes for each trano, which corresponds to an increase of 5.79%, so almost 6% on average. If we look at total optical energy, though, on the right-hand side, we can see that there's very little change. In fact, there's a very slight decrease of 0.48 femtojoules, or 0.52%. So it's harder to discern trends in the total optical energy. We can see that there are some individual magenta lines which do show an increase, but on average, there's very little change in total optical energy in the minutes leading up to tranogenesis. Again, the minimum flash area values, they're not shown in this particular area because, like we mentioned in our case studies beforehand, it remained relatively constant near its lowest value of around 64 square kilometers. I do have charts of minimum flash area that we can look at the end if we have questions, but for now, I haven't shown them because I don't think that they're super instructive, just based on the fact that they didn't change very much. So flip that on its head, and instead of looking at the 10 minutes prior to tranogenesis, let's look at the 10 minutes after trano cessation. So how does that look for the GLM graded products? Well, flash exit density, again, is in the top left, with the blue lines indicating each individual trano, and then the black line with the average. On average, we had a pretty substantial change. A decrease of 11.71 flashes on average from our 21 tranos, which corresponds to a decrease of 21.39%. And then total optical energy showed a similar significant decrease. On average, from our 21 tranos, there was a drop of 16.14 femtojoules, which corresponds to almost 16% of a drop in TOE in the 10 minutes following trano cessation, so when damage was no longer recorded from that trano. Again, we haven't shown the minimum flash area values at this point. I do have them if there are questions, but the reason we don't show them right now is because, again, they remained relatively constant near their lowest value of around 64 square kilometers. So how do these results compare to other experiments? Well, we have some really good data from the spring experiment in 2022 from the hazardous weather testbed. A team of forecasters led by Kevin Thiel from SBC and CIRO at OU, they investigated the usefulness and the value added from these changing GLM graded products in warning decision making. That group of forecasters found that they had the most utility from increasing flash counts, or FED, leading up to increasing storm severity and severe potential. One forecaster in particular reported, quote, FED and MFA were confidence boosters for me when deciding whether to issue or hang on to headlines, especially if storms were fairly marginal, end quote. So that corresponds well to our event, where the graded products, in this case, could be really substantially important for hanging on to headlines. And our storms in this case were fairly marginal, since it was a low-level tornado outbreak in late February. The survey respondents to this experimental warning program testbed session found mixed results when using TOE, or the accumulated brightness product. About 70% of those respondents rated TOE as either not at all useful or somewhat useful. And as one forecaster noted, it's not that they don't think that TOE adds value in this situation. It's just that they have a lot less confidence using it because they don't have as much experience with, say, flash exit density. And FED shows a pretty substantial increase prior to tranogenesis, and then a decrease after trano cessation. So really familiarizing forecasters with in what situations is that total optical energy product useful is something that I want to approach with this presentation. And we will compare all three graded products during the life cycle of the trano in just a moment. But one other point I want to make from this hazardous weather testbed is that they explored alternate flash extent density, or FED, color bar ranges. The final report from the experimental warning program recommended that the FED color bar maximum value be decreased from 256 flashes, which is the standard in the NWS AWIPS, down to 130 flashes. So that is fairly easy for forecasters to do. If you haven't done it yourself, I recommend you can follow these directions. Once you have the product up in AWIPS, you can right-click on that GLM FED product listing in the lower right-hand corner, and then select the option of Change Color Map, and then set that slider bar next to Color Map Range Max to 130. And that will closely align with the recommendation from the 2022 hazardous weather testbed experiment. So one forecaster in particular mentioned that from this experiment mentioned that they thought that some of the forecasters may not be very familiar with how to do that on the fly or when they should be doing that on the fly. And so one of the things I wanted to show from this presentation is that all of the GLM imagery examples of FED from the imagery that I showed for the 3 tornado case studies show a maximum value of 128 flashes, which corresponds fairly well or really well to the HWT recommendation. So that's what it would look like in your AWIPS field for this, this tornado outbreak. So like I said, we were going to do an intercomparison of all the GLM, the 3 operational GLM graded products during the life cycle of the tornado. So what we have here in the table in the top center is we've got one row for each of the GLM graded products, FED, MFA, and TOE. And then we've got the values from the 10 minutes prior to tornadogenesis on the left-hand side. We've got how the values average during the lifetime of the tornado, whether that duration was 2 minutes or 28 minutes. And then we've got on the right-hand side, those GLM graded product values, how they're changing after tornado cessation. So from right at tornado cessation to the 10 minutes after. So looking at each number individually, if the number was an increase, I have highlighted that in red. If the number was a decrease, I have highlighted that in blue. And then for each column, I have bolded the value which had the most significant change during that time period of the tornado life cycle. So the average maximum flash extent density increased by about 6% in the 10 minutes preceding tornadogenesis, while minimum MFA was unchanged and maximum TOE showed little change. All 3 of the graded products, FED, MFA, and TOE, increased by around 11 to 13% during the duration of the tornado. So we had a larger number of flash counts, a higher optical brightness, and then an increasing area of the smallest flash. After the tornado ended, I find this particularly interesting. We had an average maximum flash extent density and TOE value showing marked declines in that 10 minutes following cessation, with a drop of about 21% in FED and almost 16% in TOE. So those sharp declines in flash extent density and total optical area could be really good confidence boosters for expiring warnings or deciding to hang on to headlines as storms are looking more marginal. So in summary, there were 21 tornadoes that were tracked along with their associated GLM graded products during the February 27, 28, 2024 severe weather outbreak. The average maximum flash extent density value increased by about 6% in the 10 minutes preceding tornadogenesis, while minimum flash area and maximum total optical energy showed little change during this time period. All 3 of the graded products increased by around 11 to 13% through the duration of the tornado, and average maximum flash extent density and total optical energy showed marked declines in the 10 minutes immediately following tornado cessation, with values of about 21% and 16% respectively. So these results compare fairly well to comments from forecasters within experiments at the HWT, and I want to emphasize, excuse me, that these values may offer forecasters more confidence in issuing and then especially in expiring warnings, which we see with the drop in FED and TOE. So that concludes what I wanted to show here today. I have some extra slides in case there are questions, but I'll leave it up here on the summary and conclusions for now, and I'll be happy to take any questions or discussion.
Well, thank you, Joseph. That was an excellent presentation. Really appreciate all the information. I know I learned a lot of good stuff, especially as person that uses the flash density pretty extensively, but the other ones not so much. So it gave me, definitely some things to start to look at a little bit more, and hopefully, like you said, kind of build that confidence on, getting used to those products. Before we get into some of the questions, I do want to just give you a reminder to stay on the line and submit any questions and comments into the chat. If you do have just your first name or no name on your chat, make sure you include your full first and last name. So just in case there's things that we want to follow up with you, we'll be able to do that. And we're definitely looking for any sort of feedback, especially from field forecasters, regional headquarters, that type of thing, on ways that this information can help you out, or if you have any questions on it. Emily will be posting a link to a Google form that will allow you, if you're interested in either presenting or facilitating a future Satellite Book Club presentation. You'll find that in the chat there. I think she just posted it there. So, and then we have a reminder for a week from today, on Thursday, April 25th, Emily Maddox and John Evans will be discussing the new features and capabilities that'll be coming up in the Tower Pro version 25. That'll be coming out soon. I know I always enjoy those presentations, kind of get a nice look at what's coming up with the next update that we'll get. So definitely check that out. And then I also want to encourage everyone, if you have any questions, need any assistance, that type of thing from the Tower S team, definitely reach out to Kashad Bowman and Emily Maddox, or also find them on the Tower S channel within the NWS internal Slack workspace. I know they've been really proactive on responding to questions on there. I check that out pretty much every day. So definitely post any questions or comments that you have in that Tower S chat room. So while we're waiting for some of the chats to come in or questions to come in, there's a couple things that I wanted to kind of mention. One of the things that stood out to me, you mentioned from the hazardous weather test bed about adjusting that FED color bar maximum. That really stood out to me because even when I use that product, a lot of times I forget to make that adjustment. And, especially earlier on in events, it's tough to kind of see some of those trends or that type of thing. So, that's one big takeaway for myself, either to look into, maybe adjusting our style rules in AWIPS to set that down to 130, or, just kind of remind the forecasters how to be able to make those adjustments to be able to stand that up, make those things stand out. And then another question I had for you, you had in your charts where you had the analysis of like the TOE and that prior to tornado genesis. I noticed in the TOE, there's a really big jump with one of the events. I don't know if you had a chance to look at that where, let's see, yeah, that right chart there. Yeah, that big jump there. I don't know if you had a chance to look at that one or if you had any thoughts or comments on why that one kind of deviated from a lot of the other ones.
Yeah, that's a really good question. Obviously it's 2 to 3 times the average there at that point, so it kind of stands out. So that was from the Mundelein, Illinois EF1 tornado, and I do have an image from there. Let's see. Yeah, so this is the GLM graded product analysis from all 3 of the products during that tornado. We can see there's that huge spike in the total optical energy, accumulative brightness from that time, but we see a steady increase in FED, but nothing particularly corresponding to that time, and no particular change in the minimum flash area product. It was a fairly short-lived tornado, only 2 minutes long. It produced a very, very small amount, very minor amount of EF1 damage to an apartment complex. I looked into that tornado in particular, and I couldn't find anything that really stood out about it. What I can say is that brief increase in total optical energy may have been caused by a couple different things. It may have been caused by, say, illumination from lightning reflecting off of other nearby clouds, which may make the flash appear brighter than it was. It may have been that there was a certain amount of clearing at that point from high clouds above the storm, which led to less optical brightness being attenuated before it could reach the optical sensor in geostationary orbit. So there's a couple different explanations, but it's hard to say if there's anything specific to be gleaned about storm behavior from that increase in TOE from this one particular trio.
Thank you. Yeah. Still looking for a few more questions here. I know I'll just mention for those of you that are kind of seeing the chats, Sheldon Cusselson had shared a couple of Sierra moisture advected layer precipitable water products that kind of matched up with what you had shared at the beginning about that moisture advection that was moving into the area out ahead of the event. So definitely check out those loops. So they were some pretty good ones. And then it looks like we've got a question from Ken Cummings regarding the case summary table. Any thoughts on the reason for the higher MFA during tornadoes? Said he would expect a reduction in the MFA.
Yeah, so that's a good question. So let's walk through what that MFA analysis looks like right quick. So these are the values prior to tornado touchdown. We can see that almost all of the 21 tornadoes are at their lowest value. There's only really one tornado that modulates that upward at any point. On average, there was no change. And then during the lifetime of the tornado, there's again after tornado cessation, there's again only one tornado that's sort of modulating this upward. And then if we look at, so this is all of the 3 gridded products during the life cycle of the tornado, whether that was 2 minutes or 24 minutes or however long the longest tornado was. So the values here, we can see that the change that was substantially recorded for MFA as an increase is being pretty well modulated by just one tornado that showed that there was an increase of minimum flash area to around 350 square kilometers for one tornado as it was approaching tornado cessation, of a pretty short-lived tornado. So it's hard to say in particular if there were any, major statistically significant outcomes from minimum flash area. The only thing I can say about, you would expect it to decrease is that when you compare that to the fact that it's almost always already at its lowest value because you have a strong convective storm with an upright updraft, so you've got small in area flashes happening in a small spatial extent. It's hard to decrease from the lowest possible value, right? So that those MFA values, we see that there was an increase, but really that was just from one storm increasing, where the overwhelming majority of all the storms in this case showed a fairly constant trend at the lowest value.
Thank you. We're getting pretty close to the end time here. I'll try and sneak in another question or two real quick here. But I know there was one question from Aaron Jay. He was kind of curious if, it looked like you had done all your comparisons about tornadic storms. So if he was wondering if you had looked at any non-tornadic storms during this event and if there was any trends in the GLM data.
So I did. I actually tracked all of the values for all of the tornado warnings that were issued. So that would include warnings that did not verify, so essentially non-tornadic storms. But I didn't do a greater analysis of looking at, all the storms that were recorded that didn't have, that, maybe were just severe warned or not even severe warned. So I don't have a great answer to that comparison as tornadic versus non-tornadic storms. But I can share that from the storms that I tracked during the tornado warnings, that there was almost always, we saw an increase in flash sector density during the 10 minutes leading up to tornado genesis, and then a decrease in, leading up to warning issuance. I tracked from 10 minutes before the warning was issued, and then 10 minutes after the warning was expired. And for the vast majority of the cases, we did see an increase in FED leading up to the issuing of the warning, and then a decrease in FED as the warning was expired. So that's pretty much all I can comment on that without doing a deeper analysis.
Somebody unmute.
Steve?
Sorry, I forgot to unmute. But yeah, I don't see any other questions so far from from what we've got coming in. So at this point, since we're at our ending time, I thought we'd turn it over to Jordan for any final remarks.
All right, thank you so much, Steve. Joe, great presentation, very insightful. We're heading into that spring severe weather season. I know a lot of our field operations are getting geared up for that. There's already been a few outbreaks this year. So really appreciate you bringing that to us, and you're always welcome here at the Satellite Book Club. Hope to have you back sometime soon. Really appreciate it. As Steve has said, Emily and John from the Tower S team are going to just talk about the Tower Pro version 25 next week, Thursday at noon. So please join us then if you are interested in that. In the meantime, if you need to get a hold of our Tower S team for anything, maybe it's related to configuration of GLM, Kashad and Emily, email addresses that are there on the screen. You can also find us on the NWS internal Slack workspace, the Tower S channel. For that, thanks. We're out a few minutes over, but really appreciate everybody for sticking on the line today. Hope you'll join us again next week. Until then, have a good spring. Take care, everybody. Bye-bye.